In this numerical problem, we have been given the rotor, which was a popular ride in the fairs, where the rider was made to stand in a cylindrical room, which was then set into rotation. As it reached a certain speed, the floor of the room was removed, but due to centrifugal force and the friction, the person remained stuck to the wall. Here we have to find the minimum angular speed omega for the rotor of radius r equal to 2 meters if the coefficient of friction between the wall and common human clothing material is mu equal to 0.35. Let us analyze this situation from 2 points of view. First, for an observer outside the rotor, the rider is trying to move straight in a tangential direction, but the rotor wall is obstructing that motion, and it is compelling the rider to change the direction by exerting the normal reaction. So the normal reaction causes change in direction and ultimately circular motion. So it is playing a role of the centripetal force. But what about the rider, the observer inside the rotor? For such an observer, the surrounding, that is this whole room, is in rotational motion, and therefore it is in a state of acceleration. And a surrounding or frame of reference which is accelerated is called as the non-inertial frame of reference. What is special about them? Well, all bodies inside a non-inertial frame of reference experience force that doesn't seem to come from anywhere. Such forces are called as pseudo forces or inertial forces. In this particular context, because it is in a state of rotation, it is called as a centrifugal force. This force will make the rider feel as if he or she is getting pushed outward, and thereby he or she will get pressed against the wall, and the wall naturally will react to that with normal reaction N. Now, whenever there is a contact between two bodies and there is a tendency of relative motion, then frictional forces are created. Here the same situation is true. The person is pressed against the wall, so there is normal reaction, and as the floor is removed, the rider will also tend to slide downward due to gravity. So there is a tendency for motion also. In that situation, frictional force will be created opposing the motion, and therefore it will be in the upward direction, and its maximum magnitude will be mu, coefficient of friction, into N, the normal reaction. We can see this in a free body diagram over here. So this is the free body diagram of the rider. So this is a normal reaction coming from the wall. The weight of the person is trying to move the rider downward, and the frictional force is opposing that motion. So it is acting in the upward direction. For the rider to remain steady, we can equate the weight of the rider to the frictional force on the rider. So these two forces must at least be equal. So weight is mg, frictional force, the maximum possible, is mu into N. Now the normal reaction is serving as a centripetal force, and the expression for centripetal force is mr into omega square. There are three expressions: m v square upon r, mr omega square, and m v into omega. We use them depending upon what is given, what is to be found, and so on. Okay, so this normal reaction N is equal to the centripetal force. We can substitute this value of N from this second equation into the first equation, thereby getting mg to be equal to mu into N. N is mr omega square. Interestingly, now you can see m is on both sides, so that will get cancelled. What does it mean? It means the ride need not be designed for a person of particular weight. Person of any mass, of any size, can experience the same ride. So it is irrespective of the mass of the object there. Then we just substitute the values. G is equal to 9.8 and mu is equal to 0.35. Our radius is given as 2 meters. So omega is the only unknown quantity which can be isolated and calculated to be 35.73 rotations per minute, or 3.742 radians per second.